Well, hello, everyone. First of all, thank you for being here today with us. This is a sponsored talk, so I'll do quite a lot of developers relations and marketing rather than telling you some technical details or things like that. But the entire presentation will cover our 1 year of journey, what we have accomplished so far, what we have achieved, what we produced, what we built for the community, for the users, and so on. So let's get started. So it started officially in April 2022 with just one product we released so far, which was FIR Convolver. And we kicked this off with, together with Dr. Mix, and we made this beautiful video. You have to check this out. And at the moment of the release, we only had Windows, NVIDIA, and VST3 target platforms supported. And this is where we started, and now we already support AMD GPUs, Mac OS X operating system, audio unit platform, and M Silicon GPUs. We also have Linux support. So in terms of brand products, we started with just FIR Convolver, and through the beta program, we rolled out a couple of bundles. One was modulation bundle, another one was space and time bundle, and we have 2 more bundles in pre-release state, and 1 synth still in the final phase of the development when it comes to our brand products. We also released one product together with our partners. We have Martin Zaltek sitting right here in the second row of VSL. We actually met each other just 1 year ago at ADC 2022, and this is where our relationship originated. And so far, just 1 week ago, we released our first collaborative product, which is Vienna Powerhouse. And we still have, with the VSL, we still have a few more products to release, so stay tuned. And we have quite a lot of partners that we work together. So more product, service, and IP partnerships worked or signed reached double-digit number, covering various industries from gaming and VR to embedded and automotive. So in terms of user tractions of our brand products, we started with just 2,000 people who joined our email list from Reddit forum. And now we almost organically, we got 40,000 users of our brand products. With more products powered by GPU audio coming to market, we grow our exposure. In Pro Audio, our partners' audience exceeds double and triple thousand digits each. And we have multi-million user audience of GPU audio partners, clients, currently explore the tech possibilities through the SDK. And let's see the pre-recorded video messages from Jonathan Rowden, our CBDO, and Alexander Prokopchuk, our CTO. They will speak about our partnerships, technology use cases, and the way we build it through our SDK. All right.
Hey everybody, it's Jonathan at GPU Audio. I'm here to tell you about some exciting new use cases that we've got permission to share, and I couldn't be more excited to tell you what's going on, so let's get into it. So first up, on November 7th, VSL announced the release of Vienna Powerhouse, a new acceleration engine for VSL products, beginning with their incredible Mir Pro 3D application, which to me is the world's leading spatial stage simulator, simulating virtual stages all around the world. It's one of my personal favorite ways to mix in Atmos, actually, with its simple interface and just the ability to choose rooms and output to a Dolby Atmos mic. The workflow is awesome. So with the release of Vienna Powerhouse, GPU Audio was brought to the table as a very, very simple user experience, literally just a button on the user interface that swaps your processing over to the GPU on the computer. So VSL has given us permission to share a little bit about the opportunities that we were able to unlock for their users and for their product. So we're going to get into it just a little bit.
Hi, this is Paul Kopf. Do you often wish you had one button that provides you with magic extra powers? We have added just that to our Mir Pro 3D, and of course we're celebrating this with special pricing, not only for Vienna Powerhouse, but also for Mir Pro 3D and all 3D room packs. Here's what the Vienna Powerhouse actually does. As soon as you activate the GPU audio mode, your graphic card will take care of the lion's share of processing whenever impulse responses are involved with reverberation. And voila, your CPU is free to take care of other things. It's insane. So our new Vienna Powerhouse boosts the performance of your computer with a single click. It's one license per computer, and you should give it a go right now with the free demo license that is available on the product page. If you're running an older system, please check the system requirements. You will want a powerful graphic card with enough VRAM on Windows and a Silicon M1 or M2 processor on Mac. I don't even know what you're waiting for. Go right ahead and hit that button. Have a great day.
All right, so if you're at ADC, I think you probably already know who Vienna Symphonic Library is. Legendary company, the gold standard for virtual sample-based orchestral instruments, virtual concert hall emulations, and so much more. If you're in the world of film, TV, and game composing in particular, chances are you probably already have it installed on your laptop right now, such as I do. The VSL ecosystem serves some of the biggest composers in the world, like you probably already know, such as Ludwig Göransson, and the biggest AAA game titles in the world as well, such as the recent Hogwarts Legacy and so many others. It's also true that with great power comes the great need for great computing solutions. So we were very excited to hear that they wanted to try our SDK, and connecting with Martin on that last year at ADC has birthed some amazing results. So after getting the chance to try our SDK, we get to see how accelerated audio computing could enhance their user experience and creative output. So let's talk about the next company in our list. Mantra.io, led by Brian de Oliveira, is one of the most exciting and forward-thinking plugin companies I think that I've ever met in my life. Brian founded Mantra as a company that brings the power of game audio engines into the worlds of DAWs and live performance and composition through the intuitive, high-resolution interactive visual interfaces and incredible ultrasonic sample libraries. His interactive DSP and modulation engines are just incredible, and it makes using virtual instruments feel more like terraforming worlds of sound with the click of a button and the drag of a mouse than, turning knobs and sliders. And I just absolutely love his vision. Brian comes to the world of music from the world of gaming, with accolades from Capcom, Sony, and many other companies. His scores and his engines serving as the backdrop for games like Resident Evil Village, Shadow of the Tomb Raider, and a ton of other stuff. And here's a quick word from Brian himself.
I'm Brian de Oliveira from Lasting Creative and Mantra Instruments. For the past decade, our team has been merging music with sound design and creating immersive audio for interactive experiences across the globe. We've had the privilege of contributing to the audio in games like Resident Evil 7 and 8, Sony Streams, and Shadow of the Tomb Raider. Our goal is to craft atmospheres that resonate deeply, making every sound a vital part of the story. With our rich history in gaming, we've embraced the storytelling potential of audio. And now we're channeling these expertise into developing tools that give artists and creators new avenues for musical expression. The emergence of GPU audio has unveiled new creative possibilities for us. It's allowing us to create tools that make spatialization as dynamic and expressive as any instrument in a musician's hands. This cutting-edge technology is redefining audio production. It offers creators the precision and versatility to add narrative depth to music, a feat that used to demand extensive post-production work. In the midst of this revolution, and along with our partners Audio Echo Inc., we're developing a new tool inspired by our past achievements in gaming, but designed for the future of sound. It's crafted to enhance the creative process in an intuitive and significant way. So stay tuned for our upcoming reveal. Thanks to the capabilities of GPU audio, we're transforming our dreams into reality, and we look forward to having you join us in this exciting new chapter of musical expression. The future of sound is just around the corner, and with the power of GPU audio, we're unlocking vast new creative landscapes. I invite you all to explore and create alongside us.
So as Brian was saying before, being able to use GPU audio for them has unveiled new creative possibilities due to the amount of compute that they now have at their fingertips. As he mentioned, making spatialization a dynamic and expressive thing that is more like an instrument than a tool for reverb is really, really exciting. Additionally, being able to add precision and versatility and narrative depth to the music requires a lot of power. And that's what they're looking for. And that's what they found in GPU audio. Finally, with that amount of compute at their hands with GPU audio's parallel processing, they're able to create instruments that have enhanced expressive natures and controls that weren't necessarily possible before. So another spectacular example of GPU audio processing in the real world is for next-gen synthesis in use cases with one of my favorite types of synthesis, physical modeling. As you guys all know here and probably have a ton of expertise in, physical modeling synthesis is a technique used in digital audio and music to emulate the sound of real-world acoustic instruments and other physical systems. It does so by simulating the physical properties and behaviors of the systems through mathematical models. The models represent the interactions of various components like strings, tubes, membranes, spaces, and their responses to various excitation forces. So in particular, delay lines play a crucial role in physical modeling synthesis, being used to simulate the propagation of waves or vibrations through the modeled system. Of course, we're dealing with wave propagation, resonance, and filters. And if you add to this nonlinear functions for behaviors like string vibrations, breath pressure like wind instruments, etc., it's clear why physical modeling synthesis is viewed as the future of virtual instrumentation. So imagine our excitement when we met audio modeling, led by Emmanuel, and we could not find a more kindred spirit for the job for exploring this exciting world of synthesis. So here is audio modeling in their own words.
At Audio Modeling, we're on a mission to revolutionize music production, both in the studio and in live performance. We are innovators, which means we're always blazing a trail to new horizons. Our Camelot performance management software, proud winner of a 2023 MIDI Innovation Award, has reshaped the live performance experience by seamlessly connecting MIDI controllers to both hardware and software instruments. Our SWAMP technology, which employs both physical and behavioral modeling, is the beating heart of the most expressive and controllable virtual instruments available. From SWAM solo woodwinds to solo brass, solo strings, and our latest innovation, SWAM string sections, audio modeling redefines the limits of what's achievable in a software instrument. Our technology has evolved in tandem with the growth of computing power in modern processors. But to reach even further new frontiers, we've partnered with GPU Audio. Thanks to GPU Audio, which is bringing the power of graphics processing chips to audio developers, we're achieving unprecedented levels of precision and performance. Together, audio modeling and GPU Audio are not only enhancing existing products, but also bringing to life instruments we've always dreamt of. This is only the beginning. Join us as we embark on this journey to reinvent the ways in which music is produced and presented. Audio modeling, where innovation meets music.
So by adopting GPU audio technology for various aspects of their physical modeling components, audio modeling can unlock creative potential. By integrating this processing, they're minimizing CPU constraints and empowering the creation of more intricate and powerful virtual instruments, opening up boundless creativity in sound design. Second, they're expanding artistic horizons. Musicians, composers, and producers will gain access to a broader spectrum of expressive sounds, nurturing innovation and creativity. And third, we're opening up a new era of creativity. The partnership between audio modeling and GPU audio really signifies the inception of what we consider to be an extraordinary journey in the world of physical modeling with new compute. Limitless possibilities on the horizon for ultimate beneficiaries, and we believe those to be musicians and producers like you. Not only in the world of audio plugins for music, but GPU audio definitely has additional use cases for DSP-powered effects and processes in other areas, shall we say. So, such as hardware interfaces and multi-effects, distributed DSP, cloud platforms, embedded GPU systems, and more. In particular, there's a couple of cases I thought I'd say a couple more things about that a lot of people have been asking. So one of those would be the web service case. when it comes to web-based processing, whether it's for a DAW or for like a multiplayer experience or something like that, or broadcast, locally and remote servers and distributed DSP acceleration is super important. We can do that. Enabling DSP effects enhanced with spatial audio and other techniques for thousands or tens of thousands or hundreds of thousands of online users in voice chats, we can do that as well. If you're running voice processing for the next big Zoom platform, we can do that as well. Just offering up real-time audio effects on web-based experiences running on GPU servers, especially at scale, can save a lot of money, when it comes to AWS services and other things like that. So if you're interested and you're building a platform, definitely get in touch, and we'd love to do some research with you. Another really popular area of interest is on the embedded case. So we're talking hardware, digital hybrids, other things like this. We all use DSP interfaces and stuff like that at home for our recording studios and our project studios. But what about the next gen of that stuff? In our minds, embedded systems with GPUs are becoming more common. I mean, we're seeing them in cars. We're seeing, like AMD Ryzen AI on mobile phones and things like this. There's going to be more options for utilizing this acceleration on embedded devices, whether you're building a custom interface or if you're trying to leverage other hardware that already exists. So, for next-gen extreme low-latency audio interfaces, we see a lot of potential. Or when it comes to embedded multi-channel array of speakers, we see a lot of potential in those areas. So anywhere that hardware can be accelerated, we see a possibility there, and we'd love to talk more about those problems and how we can solve them. So none of these products or use cases would be possible without a working SDK. So it's my pleasure to pass things on to our co-founder, Alex P., to share more about how he and his team have built the essential toolbox for accelerated audio computing. Alex, take it away.
Before we move to this part of the SDK, we have quite a lot of the partnerships so far. Some of them are the evaluation phase, some of them are already in production, some of them already released so far. And what's more important about understanding this kind of relationship and partnership we build with our customers of technology, so to say, is that you have your product lineup integrated once, and you have all of your products working the same way, GPU powered. You don't need to rewrite your code from scratch. In fact, you just need to profile your application, and in the profiling report, you just need to see the most computational heavy functions that you want to offload to the GPU, whatever they are. Classic DSP or machine learning, tensors, does not matter. We can build a very tiny API for you so you can leverage the power of GPU, whatever you're doing. All right, let's move ahead with the SDK, and my partner, Alexander Prokopchuk, will tell you a little bit more about it.
Today I want to briefly introduce you to the GPU Audio SDK, the entity that made it possible to drive these partnerships. As the problem we are trying to solve here is rather complex, SDK is layered instead of being monolithic and can be utilized in various ways. The main idea is to be as broad as possible in a sense of possible applications. So if we are talking about operating systems, it would be at least Windows, Linux, and macOS. If we are talking about host or CPU architectures, it would be AMD 64 or x86 and Apple Silicon. If we are talking about device GPU architecture, it's NVIDIA, AMD, and Apple Silicon. And apart from powering the products on PCs and laptops, we of course also support turning the embedded GPUs into rather powerful DSPs, which can then be utilized in such embedded designs as speakers, headphones, personal electronic devices, etc. Now let's take a brief view of the components of the layers that GPU Audio SDK consists with. One part is the GPU Audio component itself, or audio processing engine as we call it. It consists of a low latency scheduler. This is the GPU part, which actually manages the tasks, because when we have audio processing workflows, we usually processing a huge amount of tracks, and each track can have multiple effects or processors attached to it. And the scheduler is a component that manages those tasks execution according to the current environment constraints. If we are working in real-time or monitoring scenario, we would optimize the execution for the low latency. If we are currently, for example, rendering a project from a DAW, we would, of course, optimize for throughput. As well as the scheduler audio processing engine contains the implementation of routines provided by the engine's API. There's actually quite a lot of infrastructural stuff here. And the library is a proprietary code of GPU audio, so it is provided as a binary in the form of a dynamic library, or to be more precise, actually a set of dynamic libraries. Regarding the processor API and DSP API, both of them are open header libraries, and both of them use GPU audio engine. But one of them is used to create and maintain chains and graphs of processors for processing, and the other one is utilized for actually developing a particular processor. And the last part mentioned here is DSP components library. This one contains various already implemented filters, things like partitioned convolution, delay lines, basically the usual components that everyone needs when implementing some kind of audio processing. In a way, this library is independent of GPU audio, or you may actually say vice versa. GPU audio is independent of DSP components library. You can write completely on your own the processor, utilizing only processor API and DSP API without using any components and the DSP component library. Now to the possible strategy on porting some product to the GPU. Basically, as a starter, you will have some kind of topology, some kind of the prototype which works on CPU. It may be in C++, it may be in MATLAB, it may be in Python, it doesn't really matter. But you have something, you have product design, DSP design basically. Now you have to port this code to GPU. This will introduce some additional dependencies, additional keywords, like you can see here, the _ host and device appear. We have introduced the warp context to tell our code how many threads do we have, in what context we are actually executing, and things like that. This is the first step, to basically port your code from CPU to GPU. Now that we are having our code running on the GPU, we need to run it efficiently. And for that, we need to do the platform optimization on the GPU. Here you can see a part of the implementation of the IIR state space filter. And what happened here is basically two things. One thing is that in this particular case, we know that the minimum amount of samples in a buffer that we will process is 32. That is why we are unrolling the first 32 steps of the loop in order to allow the compiler to make some pretty aggressive optimizations. And the next step is that the state space filter calculation itself was reformulated in such a way that we are in one loop iteration, we are doing single matrix versus vector multiplication, which in one step processes 2 input samples and gives us 2 output samples and 2 internal filter states, second order filter states. Because we reformulated the IIR filter calculation in such a way that it is matrix versus vector multiplication, it can be computed by the GPU very efficiently. And then, when we have such a component optimized, we usually wrap it into some kind of class and then reuse it everywhere as a part of our DSP library as a GPU SDK component, as you can see there. So, 2 main points on having yet another SDK is firstly the scheduler, which allows you to run hundreds and thousands of tasks simultaneously on a single GPU device, and the second is cross-platform capabilities. So we have unified CPU-side interfaces, how to initialize, chains, processor, memory management, copy management. If we are talking about NVIDIA and AMD, we need to copy the device from the RAM to the VRAM and back and things like that, launch configurations, environments, real-time rendering scenarios, all of this is unified in the CPU-side interfaces. And the second one is the device-side CUDA-style API. We are supporting AMD, NVIDIA and Apple Silicon, and you can write your processor once using our counterparts for things like sync thread fences, shared memory allocation, global memory allocation, thread management and things like that. Write this code once and compile it for all the target platforms. Okay, that is it with the brief introduction of the SDK. And now I want to briefly share some technical details about one of our first partnerships with VSL. This will help me to showcase the SDK from the partner point of view, using the real-world case. The product that I will be talking about is called MIR Pro 3D. I'll start with the brief product description. Vienna MIR Pro 3D is a holistic mixing and reverberation application based on groundbreaking VSL technology, multi-impulse response convolution. Not just virtual instruments, but any audio signal can be authentically placed in a multi-sampled room using the MIR, making it exceptionally easy for the user to combine all aspects of placement and reverberation into a single intuitive workflow. And now, what is the challenge here? The challenge that GPU audio resolves here comes directly from the name of the product, multi-impulse response. This means that each input channel of each audio source will be convolved with many IRs, impulse responses, not just one, which makes this product rather demanding in the sense of computational power for executed hundreds and thousands of convolutions. Here you can see the API that VSL and GPU audio agreed upon. This API is implemented between the MIR Pro 3D and the GPU audio engine. So it's above GPU audio engine and abstracts all the internal intricacies in those few very straightforward calls. Let me share some details about the call stack and environment to give you some context to better understand what happens beneath this API and what happens above it. So VSL as a client application of GPU audio implements rebuffering to guarantee that buffer length will be constant between initialized calls, as changing buffer size may lead to memory allocations and hence break the real-time constants. We usually don't want to do such things on real-time DSP processing thread. As you well know, DAWs themselves are not guaranteed to provide you with constant buffer sizes, so it's a problem that we need to solve ourselves inside the product. GPU audio convolver component internally implements double buffering. In this scenario, calling thread is virtually never blocked as it returns the result of the previous call. The problem here is that we are offloading computation to other device than CPU, hence ideally we would like to be able to return results asynchronously, but DAW interfaces do not allow us to do so, and I will talk more about it later today. GPU audio platform itself uses thread pool internally to manage and synchronize calls arriving from different clients, different instances of MIR Pro 3D in this case. The pool size can be different in various use cases, but in the end the thread count will always be close to the amount of the CPU cores available in the system. And now some details about the actual convolver processor implementation. This processor is actually quite similar to the one that we were showing earlier today during the workshop here. It uses partitioned convolution and fast FFT implementation on the GPU. Those modules are a part of the DSP library of the GPU audio SDK. The one difference between GPU convolver that we provided for VSL for MIR Pro 3D and the conventional one is of course that there are more than one impulse response per input channel, so it's a matrix of convolutions. And one additional option in the VSL convolver is to reset convolvers, which zeroes out their internal state, effectively silencing the tails from already provided signal.
And as a result of this collaboration, we already showcased this during the NAM this year. I have my own laptop, Razer Blade, 16 inches. This is the most powerful laptop you can, any money can buy, practically speaking. It has Intel Core i9 32 cores, and it's running something about 3.5 gigahertz. It's pretty beefy stuff, and it also has RTX 4090 on the board. So when we originally showcased during the NAM show, if any of you visited this NAM show, you saw that CPU mode, when CPU mode was active, we had CPU usage 78% overall system, and when we turned into the GPU mode, we went down to the 8%. For our benchmark audio project reconstructed Stravinsky Sacred. It has something around 73, 78 instruments, I don't recall exactly. And when you run this with a Dolby Atmos output 7.1.4, it's 12 channels, right? And per each channel, you have 2 convolutions, which results in more than 1,800 convolutions you need to compute real time. So these are numbers for NVIDIA Windows standard machine, and for MacBook Air, a CPU was not able to just even play it back, this audio project, but when you turned on the GPU power, you were able to basically play this back. Two more things about this collaboration. So first of all, on the QR code right here, on my right to your left, you can scan this QR code and you can find there a workshop where we discuss this integration scenario for VSL. So please take your phones and scan the QR. And for your right, this is QR code that will lead you to a sign-up form for our SDK. So the sign-up form is pretty simple. You just need to tell a little bit more about yourself. The SDK comes with the license agreement. This license agreement tells you that this SDK is provided only for the evaluation purpose for the period 6 months. Everything comes for free, and you guys just take it for evaluation purpose. And after this period expires, you just need to terminate everything. That's it. So no strings attached. And I want, in the rest of the time, in a few minutes, I want to very quickly cover a few more technical challenges our company accomplished per this year, and the next challenges that we want to encourage audio developers community to get on the board and to help us resolve. So let's start with the solved challenges. And as I said, GPU audio unifies multiple platforms, different operating systems, different driver stacks, different architectures, different target architectures of GPUs, different frameworks. Like it's literally hell. Like GPU vendors cannot do things that we do for them. And in fact, for example, for AMD, we have the SLA agreement where we co-develop stuff. Today I want to share what exact challenges we solved so far per this year. So as you already know, we support M-Silicon GPUs. And obviously the only way to do that efficiently is through Metal. Today, Metal is quite novel in all of the meanings possible framework, and it has lack of functionality when it comes to like traditional GPU programming or even like traditional shader programming. So certain device language limitations in Metal prevents us to develop efficiently, such as no inheritance, no subwarp, synchronization communication features. They were just, we had lack of those features, no sublog synchronization features, no double precision support, limited set of atomics, all pointers and member functions require special annotations. In fact, 1 year ago, there were no function pointers in Metal, which is crazy. No time basis. There were also other high-level limitations from Metal that come from the SDK. In previous macOS versions, no device pointer on the host, no easy passing of memory pointers from host to device, need a custom pointer format that works with buffer and offset. Loading different models and managing device function calls completely different than in CUDA HIP, like in regular way that most GPU developers work with. Different setup for function pointers is required. Memory model and cross-multiprocessor communication is not guaranteed in the memory model, so the scheduler, our core technology, needs to ensure communicating tasks are executed on the same multiprocessor so we don't break the context. Unified memory allows to directly access data from the CPU and the GPU. Thus, our underlying memory allocation and transfer model is completely different for Mac. We abstract all of this and we solved all of those challenges. We also need to find solutions for those issues both on scheduler level and user code level. For user code level, we abstract everything into an execution context which unifies and abstracts the underlying device functions. This allows to write all user functions in a unified way, while our abstraction layer takes care of mapping the respective higher level functions to the underlying hardware. The same goes for the HIP. For those who does not know what the HIP or HIP is, it's another technology of AMD that allows you to use CUDA source code files to target AMD GPUs, whether it's Radeon or professional GPUs or data center grade GPUs, it doesn't matter. So HAP are not available for Windows until recently. Just recently, very few devices received driver support, and it's still kind of buggy. We worked around it with DLLL from Windows GPU driver and headers generated on Linux, which is crazy. We also had all kinds of possible driver issues, consumer driver not supported previously, and pro drivers disabled APUs. No runtime linking, AMD implemented it for us later on. No graph API at the time. Well, no graph API means no consistent low latency data transfers, as you understand. We came up with alternative logic patterns that still fulfilled our latency goals. Context API for multi-threading deprecated in HAP. So we did abstraction for the desired behavior required to keep user code unified for all platforms. Also, HAP had other limitations such as missing API functions, different behavior of API functions. For example, stream destruction might cancel running kernels in HAP. I just loved it. Different host device side compilers for NVIDIA, AMD, different C++ standard adherence, different preprocessor behavior, device code limitations were no independent thread scheduling, i.e. always lockstep on AMD, no subblock sync, no hardware name barriers available, accessible on AMD, custom barriers required. This is a low-level way to synchronize threads within the same context. And getting on accurate time basis was tricky before the architecture RDNA 3, which is the latest one. Insufficiently documented ISA primitives just on the top, just as the tip of the iceberg. So we solved all of those challenges. When I say we solved all of the challenges, that for you guys means that if you want to have a good luck and try OpenCL, any shader language, CUDA, anything, Metal directly just from one platform, you will still encounter those issues. And for sure, if you want to target all of those platforms, you need some sort of unified solution as we propose. So there are still challenges to solve. First of all, we would like to address asynchronous process block call. So in the VST, it's a very common call. You guys all know it. In the audio unit, there is equivalent for this in Juicy as well, in CLAP, and in AX standard as well. All major audio plugin vendors offer blocking process calls in their formats. A major change is required to unlock the full potential of GPU audio. What now is happening, the DAWs randomly call the processing calls, treating various buffer lengths all of the time. This is crazy. And like accessing the one single resource such as GPU is just crazy, but we still manage to do these things. Imagine if we do this properly. Because right now when you call it, it's just like you're just waiting for GPU to respond, you're consuming CPU cycles, which is another crazy part of it. And batch processing, this is something as the ability to get information regarding where an individual process block originates from would greatly increase utilization of the GPU. Offline processing, where we could get data faster than real time and work on a larger set of data, and we can render projects of your users like that, not waiting for, I don't know, hours. When all chunks from the tracks have been received, a heuristic on the side of GPU audio can then determine the best possible launch configuration. Our end goal, being able to tell when we have received all buffers that need to be rendered, which tracks and plugin instances they originate from, and the process from which they are coming. This is the proposal, which is very abstract proposal on the API that needs to be integrated on the side of standards. I'm pretty sure Bitwig guys and CLAP developers that are here today, maybe in this audience, I just don't see you. I hope Steinberg guys as well, Apple guys as well, Avid, if you are here, please take a look at this. There's a tiny API, and if you guys can make it supported by the DAWs, all of the DAWs already work with the graphs, right? If you just make it compatible, you will have zero CPU, chill CPU when you do whatever you want on the GPU, including machine learning, including any kind of DSP that was not possible before on the CPU. So as expected result, we, as I said, expect zero almost 0% CPU usage when we do engage with the GPU, regardless on the schematics engaging with GPU. And we want to unlock the potential of bringing asynchronous processing that will minimize the thread synchronization overhead. There will be no additional buffering techniques will be needed for plugin developers, and batch processing would allow better saturation of the GPU's resources, significantly lower CPU usage and faster offline processing. So thank you for having me today. And if I still have a few minutes for a Q&A session, I would like to take questions.